Hello. Hello. Can you hear me? Can you hear me well? All right. We're joining. Oh, perfect. Okay, good. Good to see. Today we're going to talk about refraction. So we have the optics assignment, which is due by the end of this week. So if you have any particular questions on the assignment, I'm happy to answer. I have about five questions and two fun questions. So five difficult-ish questions and then two fun questions that I want to go through. We're going to discuss a paradox, why the moon looks bigger when it's full. Okay. So let's have a look. I'll share my screen. Okay, perfect. So problem one. A bent rod is bent. A bent rod is bent. Okay, yes, thank you. Bent rod is partly submerged in water such that to an observer looking along the dry part of the rod, it appears to be straight at an angle alpha. What is the angle at which the rod is bent? What is the angle beta at which the rod is bent? So this is difficult to imagine without drawing. So let's draw this. So you have water. Let's start with drawing water. Bam. And then we need to draw a rod. A rod, let's make it brown, like a stick. Well, it's not like that. It's like this. It goes like this, and it's bent. But to a person, it looks like the rod is like this. to a person looking from here. A person looking along the dry part of the rod, it looks like it is a straight line, and the angle is alpha. And we need to find this angle, beta. Does everyone understand the question? Because that's sort of the hard bit here. Okay. So because we're looking along the rod, we can direct the light along the rod as well. So let's choose a color. Let's choose a pink color. And we can see that the light going along the rod goes like this, and then goes into the eye of the observer. And we can immediately see a very simple theta 1, theta 2, Snell's law, of course, sine theta 1, theta 1 divided by sine theta 2 is equal to n, the refractive index of water. And we know that the refractive index of water is well, 1.33. Doesn't really matter what it is, because they're not asking us for a numerical answer. The answer will be in terms of n. Okay. So what's happening? We see the light is coming from, let's say, from this end of the stick. The end is the light is going like this, and it's emerging like this. As I mentioned 2 weeks ago in our webinar, our brain thinks that light travels in straight lines. This is so embedded in our brain that we are more likely to see a headless person rather than to believe that light doesn't travel in straight lines. Okay. The headless person illusion, which I discussed last time. Let's have a look. Yes. We believe the fact, our brain believes the fact that light travels in straight lines. And this belief is so strong that we'd rather see that the person has no head rather than believing that light doesn't travel in straight lines. This is what's happening here. Okay, so here the refraction changes the direction of light, deviating from a straight line, and the same thing is happening here. We have a rod. The light travels along the pink line here, but our brain believes that the light is coming from here. So this is the actual position of rod, and this is the apparent position. Okay, and then then the maths becomes simple once you've drawn this carefully. Simple. So here theta 1 is pi over 2 minus alpha, and theta 2, the angle theta 2, well, that's going to be, so this is alpha, and so this is pi over 2 minus alpha plus beta, like this. All right, so from here we can write down sine pi over 2 minus alpha over sine pi over 2 minus alpha plus beta equals n. What is sine pi over 2 minus alpha? Somebody help me. Maths assignment 2. Sine pi over cos alpha. Well done. So from here, you can say cos alpha. And here we can say this is cos alpha plus beta. Cos alpha plus beta equals n. Now, this is the part where we're looking for beta. And this is where a good mathematics student would remember that cos alpha plus beta is cos alpha cos beta minus sine alpha sine beta. But this won't bring us anywhere because you'll still have to deal with cos and sine alpha. So we need a different way. So cos alpha plus beta equals cos alpha over n. So alpha plus beta is going to be arc cos alpha over n and beta. We can do this because we know that alpha plus beta have to be less than 90. So it's the first quadrant, therefore we can just use arc cos. Beta is equal to arc cos alpha over n minus alpha. And this is the answer. This is the answer. I know it's quite unsettling. So let's just introduce some numbers. So let's say, so water, we know that water is 1.33. Pure water is 1.33. And alpha, let's say alpha is 30 degrees. 30 degrees. So let's have a look. Beta is going to be arc cos 30 divided by 1.33 minus 30 and arc cos fraction cos 30 close bracket 1.33 bracket minus 30 19.4 degrees, which seems very reasonable. If the angle is 30 degrees, this is 19.4 degrees. So this is the angle at which this stick is bent or broken, however you like to look at it. So what the stick actually looks like, just recapping, this is how the stick actually is, and this is how it looks like. So how it is how it appears. Okay. Right. Any questions? Any questions here? Okay. Right. The second question is a little bit more complicated, and let's see what we can do here. What makes this question complicated is maths and geometry, not physics. The physics is quite simple. A ray of light traveling vertically hits a glass plate at an angle alpha. As a result of multiple reflections, a series of bright spots is visible on the screen. Find the distance between the bright spots. Can somebody help me with that? Like, why would there be multiple? How do you understand the multiple bright spots? Was anyone? Does anyone want to join and actually draw them? I'm sure that's an easy one to do. Can somebody help me? So why do we see multiple spots? You need to trace the ray. This is the screen. This is the glass, and light comes in. Light comes in like this. It is not because of different wavelengths. No, good idea. That would, you would see because multiple wavelengths. That would be, yeah, that's another thing. You would see a dispersion pattern. Basically, you would see a spectrum of colors. But let's say we're talking about monochromatic light. Actually, you know what? I'm thinking we could bending light. I think we can recreate this. Well, you know what? Before we start recreating it, let's see. So first, the ray will be refracted. The ray would be refracted like this, and then it will escape the glass traveling vertically. But at this end, there's not only refraction, but there's also reflection. It will reflect like this. It will reflect like this again. And now it will refract again. It will travel like this. Here it will reflect again. Some of the light will certainly escape. So here, light would travel like this, probably. Yeah, like this. Travel like this again. And reflect. Reflect again. And here it would refract again. So that's the reason why you would see bright spots on the screen. Bright spot, bright spot, bright spot. Does everyone understand why you see bright spots on the screen? Yes or no? Yes. Good. Let's see if we can recreate this using the simulation. So a glass, a vertical ray of light, vertical ray of light, and the glass placed at an angle. Oh, you can actually see it. Look. Ray of light. Ray of light. Traveling like this. Some of it is reflected. Some of it goes through. Then some of it is reflected again. Then reflected again. And it goes through. And goes through. And then here, this would be reflected again. Reflected again. And go straight through. Etc. Okay. And if you use white light, nothing really changes. It's the same idea. Same idea. Interestingly. Oh wow. That's quite cool. But you can see dispersion of light. So light breaks into into a spectrum of colors. Oh, that's very fun. Okay, I can do this forever. Anyways, we've done the interesting. Well, we've done the very physicsy part, my favorite part, and let's dig into some maths, because maths is unavoidable here, and perhaps the hardest thing in optics is geometry. Okay, so let's have a look. You have the angle at which it strikes the glass, and that angle is alpha. This is the angle to the normal. So we'll draw this the normal. Okay, and this angle is alpha. And let's label this angle. This angle is beta. Beta. Now this angle is alpha. I would like to know this angle. And it looks like this angle is going to be alpha as well. How do I know? Well, because if this is the normal, this is the vertical line, this is the normal, and this is a vertical line, and the normal, that's alpha. That means this is pi over 2 minus alpha. That means this is alpha as well. Do make a separate diagram and convince yourself that this angle is indeed alpha. One trick to make your life easier is whenever you're drawing an angle in physics, make sure you draw a very sharp angle. So not like I did, but let's say I did the same thing, but the angle like this. Maybe that's too much, but like this. Okay. So now if I take this and this angle is alpha, the smaller angle is pi over 2 minus alpha. So if I draw a triangle like this is 90 degrees. So either this is alpha or this is alpha. Well, obviously this is alpha and this is 90 minus alpha. Compare this let's make a separate. Y draw. Very acute, very sharp angles. Sharp angles. So let's say this this angle is alpha, so this is alpha, and this is 90 minus alpha. 90 minus alpha, and it's very obvious which one is which. However, if you make an angle which is not very sharp, let's say an angle like this, which is close to 45 degrees, and this angle is alpha, not this, but need the normal. If this angle is alpha, and you draw a triangle like this, you have a very hard time figuring out which is alpha and which is pi 90 minus alpha. Yeah, which is alpha? Which is alpha? Do you understand what I'm talking about? Yes or no, please. Don't be shy. So if you make like when you do mechanics and maths, they often teach you to draw a big angle, like 45-degree angle. Honestly, I don't think it's a good idea. Always draw a small angle, because then it will be very obvious to you which angle is the same, and you don't have to use similarity of triangles to prove it or anything. So I've used a reasonably sharp angle here. So alpha is this one. This is alpha. Right. So if this is alpha, I draw a triangle like this. It's a different color. It's a different color. This is beta. This is beta. And we know that the width of the plate is h. I don't know if I've mentioned that, but it is h. All right. Yes, it's in the diagram. It's h. So this side is going to be h tan beta. H tan beta. And this distance between them, let's call it delta L. Delta L is going to be 2h tan beta. That's this side, times cos alpha. Times cos alpha. And yeah, this is just a bit of trig, nothing serious. Delta L, that we just need to figure out tan beta, and we can work this out from alpha. So delta L. Oh, I forgot to give the measurements. Well, okay, let's do the sides. 2h tan beta. So well, before, So we've established that delta L is 2h tan beta cos alpha. We've established that. Now, we know h, we know alpha, we don't know beta. So sine alpha divided by sine beta is n, the refractive index of glass. That's the Snell's law. My trick in using the Snell's law, I know that n is greater than 1. And I know that alpha is greater than beta. So it's either sine alpha over sine beta equals n, or it's sine beta over sine alpha equals n. I always use the bigger angle at the top and so the smaller angle at the bottom. And that makes sense because n is always greater than 1. So when using the Snell's law, just keep in mind, since alpha is greater than beta and n is greater than 1, it makes sense. That's a shortcut. Sense. Because writing sine theta 1 n 1 sine theta 1 equals n2 sine theta 2 is usually a mouthful. Okay, it's very easy to get confused. So in a simple scenarios, when you have just one refraction, you could just use the GCSE version of the Snell's law. So I hope that makes sense. And see here, so here we can find sine beta is equal to sine alpha over n. Okay, cos beta is going to be 1 minus sine squared beta square root. I don't need to worry about the plus minus because we are dealing with angles less than 90 degrees. So the plus minus here is not needed. And that's going to be 1 minus sine squared alpha over n squared square root. So from here I can work out tan beta. Tan beta is sine alpha over n. I multiply n square root sine alpha over n squared minus sine squared alpha. So the distance between the two, between the rays, delta L, is 2h sine alpha over square root n squared minus sine squared alpha multiplied by cos alpha. This is the solution. And something I forgot to add, that h is 1 centimeter, n is 1.41, I believe. Oh, apologies. So where is it? Where is it? Oh, 1.73. The refractive index of glass was 1.73. This was 1 centimeter and 1 centimeter, and alpha was 60 degrees. 60 degrees. So we just plug that in. So it's 2 times 1 centimeter times sine 60 cos 60 over square root 1.73 squared. 1.73 squared is 3 minus sine squared alpha minus 3 over 2. Minus 3 over 2 because sine 60 is 3 over 2. So it's going to be sine 120. Oh. Interesting. Well, anyways, it's going to be 0.58 centimeters, approximately, of course. Yeah, that's it. Any questions? Any questions here? So as you can see, the physics. As in any physics problem, first you have to understand what's going on. You have to draw a diagram, and then you can start doing the maths. Which part of the problem do you find more challenging? The physics part, where you need to realize what's going on, or the maths part, where you need to use geometry to figure out the distances? You personally, can I get a vote, please? Physics or physics? Okay, that's interesting. That's an interesting thing, because for me, the maths, I immediately do the physics bit, and then I don't struggle to work through the maths, but I really find it tedious, and it's just trying to make sense of it. That's an interesting thing. An interesting thing. Okay, let's have a look here. Perhaps I'd like you to draw a diagram first, and then I will draw a diagram, and we'll see if we have the same result. Okay, if you want to draw it here on the board, just type your I drew name, and I'll give you access to edit the board. So I'd like you to spend 2-3 minutes to draw the diagram, and see if you can solve the physics part of this problem. So a parallel beam of light is incident on a glass hemisphere. So this is light incident on a hemisphere. And you need to find the radius of the bright spot, which can be seen on the screen. This is the screen. So why would you see? So if anyone wants to draw on the board, I'm happy to give you access to do that. I just need your name, which is here. Which one of these are you? And I'm happy to do that. you could use PhET to help you. Oh, it actually has. Okay, have you drawn the diagram? Yes or no? Sorts. Good. So, Alexandra, do you understand the limitation? So why would there be a?
I think it's got to do with the critical angle.
It
So
does, yeah.
when the incoming beam is like sufficiently close to like the edge of the semicircle, then the critical angle, the angle between the ray and the normal, will be sufficiently large that it won't go through and it will totally internally reflect, and therefore that ray won't pass onto the screen and you won't get a spot. So
Exactly.
radius, but I think
Yeah, so if you place a screen here, look, out of the 5 rays, 4 of them are totally internally reflected, and only 1 of them is actually going through. So all the rays up to this point would be internally reflected, and only the beam that here or closer to the center gets through. And as it gets through, it gets refracted. So you kind of need to figure out where the screen is. So you need to figure out where the point of intersection is. So where do they meet, basically. And let's have a look. So this beam, for example, this beam would be totally internally reflected. So we're not interested in that one. So we need to find the first beam that will actually go through. And it goes like this, bam, and then at 90 degrees. It is a tangent. And then, of course, there's a ray like this. Well, okay, for simplicity, let's draw it here. Okay. So ray number 1 going like this, and then refracted like this. The ray number 2 going like this and refracted like this. We need to find where this point is. So let's label this. Let's call it X. All right. So and then we start doing some math bits. Okay. So this is the radius. So that's R. And this angle is the critical angle. So we need to find the critical angle. Sine of the critical angle is 1/n. So that's 1/1.41, which is actually square root of 2/2 approximately. So the critical angle is approximately 45 degrees. Okay, that's helpful. So this is R. Well, R is 2. So X is going to be R. So if this angle is 45, so this is 45, and this is 45, and this is 45. So they are 45-degree angles. So this side X is going to be R over cos 45, which is going to be 2 over square root of 2/2, which is 4 divided by square root of 2, which is 2.82 approximately centimeters. So X is 2.82 centimeters, and the screen is placed 4.8 centimeters from the center. Therefore, the screen is behind. So we don't know we didn't know whether the screen was here, or the screen was here, or the screen was here. So the screen, if you place the screen here, the radius would be 0. If you place the screen here, that's one story. And if the screen is here, that's another scenario. And we have confirmed that 2.82, so this point where the rays intersect is actually closer. So this ray is the furthest ray from the center that gets through. We need to find where it intersects the ray going through the middle. And that's the point of intersection is here. So what we found is we found this point. And we worked out that the screen is here. And then it's just a simple matter of some trig to figure out that this is X 2.82. Then we know that the distance is 4.82. Therefore, this distance is 2 centimeters. And we've already worked out that the angle is 45. So this is 45 as well. And this is 45. So the radius of the bright spot is 2 centimeters. We have a bright spot. This is your bright spot on the screen. And its radius is 2 centimeters. So the answer is 2 centimeters. Oh, okay. Was anyone able to do this problem before I did? So was anyone able to solve it by themselves, basically? Okay, that's good. Yeah, you had the correct idea. Yeah, so well done. Okay. Problem 4. A source of diffuse light is placed at one end of a thin, long optical fiber. Long optical fiber with a refractive index of 1.2. A screen is placed 5 centimeters from the opposite end. So this is the optical fiber. This is the optical fiber. And this is the screen. You need to find the diameter of the bright spot on the screen. How would you approach this problem? So why would there be a bright spot on the screen? What's your idea? Feel free to shout out. Feel free to type. Why would there be a limited bright spot on the screen? To understand this question better, imagine a scenario. You have a swimming pool. Swimming pool. This is a swimming pool. View from the, well, this is the bottom of the swimming pool. And this is you. Okay. And the water is here. Okay. All right, let's not be cruel. You're floating. Okay. I hope that makes sense. So this is the water level. Imagine the swimming pool is empty. It's an empty pool. You have, so the swimming pool is a building. So there's walls, roof, a ceiling, and wall. So this is wall, ceiling. You place a light source. You place a light source in the middle of the pool. And the light would shine like this. So basically, this part of the wall and floor would not be lit. And this part of the floor and this part of the wall would not be lit. But this part of the wall and ceiling, they would be lit. Okay? Does that make sense? Do ask me a question if it doesn't. And now consider the same situation, but the swimming pool is full. Swimming pool is full. And there is water. Water in the pool. The light will now propagate as follows. Straight, then bam, and refracted, bam, and refracted, bam, and refracted. So pretty much the whole of the swimming pool would be lit because of refraction. I might have said diffraction earlier, please ignore that. Refraction, of course. Because light is refracted, most of the ceiling, also most of the wall is now lit. Everything except just the floor. Pretty much the floor, just the floor is not lit. Not lit up. That's why if you place a light source behind a bottle of water, you get a very, very nice, very nice lighting in all of your room. So if you've never tried this before, take your phone and a bottle of water, and place your phone next to the bottle of water, switch the lights off, and you will see that the whole room is illuminated by your flashlight. So why have I spent 5 minutes on this? Well, because if you imagine that this is made of glass, this is made of glass, this is glass, and there's light, and if the light is traveling in all directions, like the light source, so it should travel in all directions here. So there should not be a limit. It should cover an infinite bright. So it should be a bright spot of infinite size. If the light was traveling in all directions inside the fiber. So what is the limitation? Why is there a limited spot? Why is the spot limited? What is limiting the spot? Okay, nuance. Imagine two optical fibers and light. First, the light is traveling like this. And in the second optical fiber, light is traveling like this. Which beam will reach to the other end? Which ray of light, A or B, will reach the other end? B. Can you explain? Yes, because the angle is greater than the critical. So A will be reflected as well, of course. A will bounce back and forth. But the problem is that every time it bounces, some of the light will escape. 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 And by the time it reaches the other end, there might not be any visible light at all, because most of the light will escape through the walls. Whereas in B, light is totally internally reflected, and it will travel like this. No light escapes. So some light escapes. Light escapes. No light escapes. So this is what's going on. Not all light is allowed to travel through the optical fiber. So inside the optical fiber, we will have light that is only traveling at specific angles. in particular, if we take an optical fiber, the light has to travel. Oh, it doesn't really matter how we draw it, but this angle, let's call this angle θ1. θ1. And when this it hits like this, so θ1, this, we'll call this θ2, θ2, and when it escapes, it's going to be θ3. θ3. And we know that θ1 is the critical angle. We know that sine θ1 is 1/n. Because θ1 is critical. θ1 is critical. Okay. Therefore, sine θ1 is 1/n. So we can say that this is 1, this is n. So this side of this triangle is square root of n squared minus 1. Right. Now for this, we will write Snell's law. Sine θ3 divided by sine θ2 is going to be equal n, the refractive index. And the radius, because it's a long, the important thing, it's long, that means the light, the light that can escape will escape because of multiple reflections. There will be enough reflections for all the light that can escape to escape. That's why the long is an important word in this question. The thin bit means that the thickness of the thing doesn't play a role. So it's just a point. So the end point. So here, this side is very, very small. So basically what we need is this is L, this is θ3, and this is the radius. Well, the diameter of the spot, is going to be 2 times L times tan θ3. 2L tan θ3. That's the diameter of the spot. And from here, we can see sine θ3 is sine θ3 is n sine θ2. And θ2, well, it's this angle. This is θ2. So sine θ2 is, so n multiplied by square root of n squared minus 1 over n, interestingly. So that's that. So the square root of n squared minus 1. Now cos θ3, that's 1 minus sine squared θ3, square root. So that's going to be 1 minus n squared minus 1. So it's 2 minus sine, 2 minus n squared, square root. So tan θ3 is equal to square root n squared minus 1, square root of 2 minus n squared. And you sub that in, so 2L multiplied by square root of n squared minus 1, square root of 2 minus n squared. Okay, and if we calculate that, the diameter of the bright spot is approximately should be 8.9 centimeters. 8.9 centimeters. I'll leave this to you. We are running out of time. And we have one serious problem to go and two just fun things to do. Discuss briefly core cladding and multipath dispersion. So this is an interesting thing. You've probably heard that optical fibers consist of the core and the cladding. So let's say Phil. Basically, an optical fiber looks like this. And as opposed to just the core. So what we are comparing, we're comparing the core and the cladding. So in the first case scenario, so let's say the core is 1.51, the refractive index, and the cladding is 1.50. Here, the core is n equals 1.51, and then we have the air, which is 1. We can find the critical angle for both scenarios. So let's say we have a optical fiber with a core and cladding, and here we have an optical fiber with just a core, just a glass rod. So what's the critical angle in scenario 2? What's the critical angle? Can somebody calculate really quickly? Yeah, 41.5. I'll just double check. 41.5 degrees. Yes, very good. 41.5 degrees. And what's the critical angle in the first scenario? Like C1, C2. What's the critical angle in the first scenario? $83.4. Very good. Thank you. Does everyone understand why? So why is, I just had one yes. Can I hear from the rest of you guys, please? So Victoria, Andre, Edith. Okay. Why is a large critical angle beneficial for an optical fiber? Because effectively what that means, that if light travels like this, it will bounce. Will bounce. But if light travels like this, if light travels like this, it would still bounce. Because the critical angle is anything above 40, it will bounce. But whereas here, the red light would go through because it's more than 83. So the red light goes through. Not the red light, it's not necessarily red, it's just the red beam. But the green one would escape the green one would certainly not be less than 83. It would escape through the cladding, and it would not get through. Yes, that would mostly quicker transition. Yes, that would make a quicker transition. Why it is beneficial for light? So this light this light escapes. Only angles close to 90 are allowed. And here angles up to angles 41 and above. 41 and above. There will be less additional distance if we went straight through the core. True. So you understand that the two beams travel a different path, and that's very important. So suppose there are two paths, two pathways for the signal to travel. The first path is like this, path 1, like this. And the second path is like this. So the green path, I shouldn't write the word green in red. Green path takes more time. And effectively, that means a signal. If you send a signal, would split. So if this is the time scale or the distance, this is the signal that you sent. This is the emitted signal. But because this signal is allowed to travel along two different paths, one signal, so the part of the signal that travels along the green path would be with lag behind the red signal. The signal that took the red path is quicker. Red is quicker, not the red. So I don't want you to confuse, not red light. We're not talking about red and green light. It's just the red path. Red path is quicker, and this is the green path. So you are sending a signal. Let's say you're sending the signal 1, and what does the other computer receive? They receive 1, 1. And last time I checked, 1, 1 is not the same thing as 1. This is called multipath dispersion. Is when your signal is altered because it is allowed to take two different paths. So this is called a multipath dispersion. Multipath dispersion. I think I'll try to make it the green path, because what would happen is, because it's not, you're not given two different paths. You're sending a signal. So what is actually happening? You're sending a signal, simple signal, but it gets split into multiple signals. So overall, you would have an overarching signal like this. Transmitted signal. Transmitted. So no, emitted. Emitted. And this is received. Received. So let's say you're sending 1, 0, 1, 1. So you're sending 1, 0, 1, 1. This is the number, what, 8 plus 3. This is the number 11 in binary, as I believe. This is the number 11 in binary. And what you are receiving is you're receiving blob, no blob, blob, blob. It would be very difficult to figure out what you have received. Okay, does that make sense? Because the signal will spread out because of all the paths that the different parts of the signal have traveled through, and rather than receiving a sharp 1, 0, 1, 1, you would have three blobs of signal, which would be very difficult to discriminate. So you either have to increase the time interval between the signals so you don't have overlapping of the signals, or you have to only allow the signal to travel in a very narrow range of paths which have very, very similar time. And this is the main purpose of the cladding. The main purpose of the cladding is to reduce to increase the critical angle in order to reduce the time difference between the different paths taken by the signal. So it effectively removes part of the signal in order to make it cleaner, which is wonderful. I mean, it does mean that you need a more powerful laser just to begin with, because some of the light would escape, or actually use a laser beam with very narrow spray angle. It's not a spray angle. Anyways, next question. A short one and an easy one. So time to relax. Refraction in the atmosphere causes an error in determining the position of a satellite. For a satellite at 45 degrees, the error is 2 minutes. Find the refractive index of the atmosphere for radio waves. Okay, so first of all, does everyone know what a minute is? Oh, okay. I'm very glad, actually, because I get you to teach something. A minute is a 60th of a degree. So 1 minute is 1/60th degrees. Very simple. So for example, if you go to a Google map,
Yeah, doesn't give you the coordinates. Coordinates. Okay. So Giza Pyramid Complex. I hope you know that the coordinates on the GPS coordinates are written in degrees, and it's equal to 29 degrees, 58 minutes, and 34 seconds. So a second, of course. So 1 second is 1/60th of a minute. 1/60th of a minute, which is 1/3600th of a degree. Just so that you understand this notation. So when we say 1 minute, we mean 1/60th of a degree, unless if we actually mean 1 minute, which is so 1/60th of an hour, or in general, a minute is 1/60th of something. Okay. Right. So if you have, the atmosphere of the Earth, and this is your antenna. This is your antenna. And this is the satellite. And the radio signal travels from the satellite to the antenna, and there is a small refraction because of the atmosphere. Now, it doesn't happen in the top layers, actually. It actually happens gradually. If you think about it, because the atmosphere becomes denser and denser. So actually what happens is it travels like this and then bends like this. But one of the problems that you've done, what you should have done in the assignment, is actually to see that even if it's a gradual bending, the Snell's law still applies. Okay, so this is θ1, and this is θ2. Now, what does it mean that the position? Well, the position of the satellite. We think that the satellite is here because the radio signal is coming along the purple. We think that the light signal is coming along the purple line. Oh no, we're not. Sorry, we're not thinking that it's coming from the purple line. We're thinking that it's coming from the tangent, so where the antenna is pointing. So we're thinking more like here. Well, anyways, I mean this bent part is very small. So effectively, what do we say here? Well, we say that there's the antenna. So sine θ1 over sine θ2, using the Snell's law, θ2 is equal to is equal to the refractive index.
And theta 1 is 45 degrees. So it's going to be sine 45 degrees. So 2 minutes is 2/60th of a degree, which is 0.2/60th, 0.0333 degrees. And so theta 1 is 45 degrees, and theta 2 must be, it's slightly smaller. So it's sine 45 minus 0.033 degrees. And if you work it out, it's going to be 1.00058. So the refractive index of air for radio waves is approximately that. So what it means, it gives you an error. You point your antenna at a point in the sky, and this is where you think the radio signal is. Well, actually, it's not. Okay, so we think it is coming from that angle. It's actually coming from that angle. Right. The next thing, so this is due to the refraction in the atmosphere. The refraction in the atmosphere. Refraction in the atmosphere. Look at these two pictures. Refraction and diffraction are often quoted when explaining the full moon paradox. So what the full moon paradox is that when the full moon is when you have moonrise, when the moon is rising, and moon is rising, the full moon is always rising immediately after the sun is setting. And if you think about it, it has to be that way, right? So if it's a full moon, the moon will rise immediately when the sun sets. So the sun sets behind you and the moon rises. So early in the evening, you can see this full moon, and it looks massive. It looks absolutely huge. And does anyone know why? Does anyone know why it looks so huge? And I've attached two pictures. I've tried to make it that this building, which looks like the Empire State Building, it might not be, but I tried to make the scale approximately the same. So you can see the scale of this building. Actually, no, like these two buildings are roughly the same scale. But you can see that the moon looks much more massive. So what I'm comparing it to, I'm comparing these two buildings, and I'm comparing the size of the moon, and you can see that this moon looks absolutely massive. Does anyone know why? Well, the easiest explanation would be that, well, the way the picture is taken, this building is actually further away. So the scale is, it's wrong to adjust it like this. I have to adjust it so that the size of the moon is the same. So I have to adjust it like this, roughly. So just further away. And this kind of gives you the answer. So if you think about it, the size of the moon has to be the same. There's no way the moon can be different size in different parts of the sky, because the moon is so. The moon, you will often see that, oh, it is a super moon, and it looks huge. The moon gets refracted by the atmosphere. No, sorry. So the thing is, it's not refraction, it's not diffraction, it's not anything like that. It's actually an optical illusion. It does not look bigger. It seems bigger, but it is not actually bigger. And you can easily check that. If you take a 1 penny coin and you place it, and you take a 1 penny coin and you place it in front of your eyes, and you try to close the moon. By the way, what is the phase of the moon? Moon phase. Okay, yeah, today is a good day to check out the moon. So you take a 1 penny coin, and the weather is permitting. So take a 1 penny coin and see how far you need to hold it in order to close the moon, to cover the moon. You can measure that distance. And then do the same when the moon is high above in the sky, and you will find that the distance that you have to hold it is exactly the same. The moon does not get closer to the Earth. Well, it gets a tiny bit closer, but not... has nothing to do with the moon's orbit, has nothing to do with the distance from the Earth to the moon. That is pretty much constant. That changes by maybe 1 or 2%. The reason is the buildings. The buildings make it look like the moon is bigger. When the moon is on the horizon, we tend to think that it is further away, because things on the horizon, to us, we are used to things that on the horizon are further away. And things are right above you, they're closer to you. So we see the moon the same size, but when it is on the horizon, we think it is further away, therefore it is bigger. Okay. So what happens with our perception? And it's a really fun thing to think about. Because when the moon is on the horizon, we know that these buildings are very, very far away. And we think that because they are far away, the moon has to be, and the moon is massive compared to them, the moon is big. Whereas when it's high above in the sky, when it's high above in the sky, our brain thinks the moon is actually closer to you, and automatically makes your brain think that it is smaller, whereas actually it is absolutely the same size. So do experiment, like tonight, moonrise, moon Moonrise today, London. Moonrise. Okay, 4:40 p.m. in the east. So if you find east and the moon is actually up already. So after this session, go outside, find a 1 penny coin and measure the distance. So what you literally do, you take a 1 penny coin and you measure. You cover the whole moon so that exactly covers the moon, and you measure the distance that you need. Okay, you might need a longer ruler than that. And then do the same experiment when the moon is really high above and the moon is really low. When it looks that the moon is massive, do the same experiment and you will find that the distance is always the same. It doesn't change. Well, it changes slightly, but you'll never be able to measure this difference. So when the moon looks massive, it's actually not. And that's brilliant. Okay, so that's it. That's it for today. Hope that was useful-ish. And I'll see you. Question 13 on physics. Question 13 on physics. I think so. Let me have a look. Documents, assignments. So physics. Sonnet. Yeah, you differentiate it with respect to alpha. Yeah. Sorry, if you. Yes. Yeah, it won't. There is a maximum, and yeah, the answer should be in terms of n. In terms of n. Okay.